on arc length and speed. So first of all, we'll go over arc length. So arc length is the length of a path. So length of a path, okay? And I'll give you the formula for that. So length of a path, aka arc length. So I'll put arc length here. Length. That's going to be, it's usually denoted S, okay, is equal to the arc length of a path, okay? So again, I'll write arc length of path. And remember, well, in a previous video, I explained the difference between a curve and a path. And I will do so again briefly in later on in this slide. Okay, so here's the formula for arc length. I'll just put it out there right now. So it's the integral from a to b of r prime of the magnitude of r prime of t and then dt. Okay, so this again, I'll go over the difference between a curve and a path. This means, like, let's say we have some curve. It looks like this. Okay, and here's r of a. So this is where it starts. And then here's our r of b. But, so the curve might only go one direction, in the, like, all the way to the right, and then once, and then stop there, which then, in that case, it would be the arc length of the curve as well. But for a path, it can go backwards. So, like, let's say it's going this way, we're traveling this way as t increases beyond a. But then at this point or something, we start backtracking. So then we start going over the same path but in a different direction, going over the same curve, right? And then once we get to this point, we go back and continue on all the way to r of b. So anyways, the concept behind this is that this arc length is not of the curve itself. That would only be if you were traveling unidirectionally, meaning in one direction, right, the entire time, and not backtracking or anything like that. But paths, or the path, r of t, may allow us to do that, like backtrack. So it might end up being more than the arc length of the curve. Okay, so this is basically, so another way to phrase it is that this is how far one travels from, let me see if I can spell here, from t equals a to t equals b. Okay, so basically, if you're following r of t, r arrow of t, and you're walking as it tells you to, and then you stop here, right? We're walking to the right, and then you stop, and because then r of t tells you to walk back some, and then turn around again and continue forward. Then that would be how far you traveled. Okay. All right. So I'll expand on this formula here and show you, break it down a little bit. So S is equal to, S, our arc length of the path, is equal to the integral from a to b of magnitude of r prime of t and then dt. Okay, so this is also equal to the following. If we look at it component-wise, then we have the integral from a to b of the magnitude of x prime of t, y prime of t, and z prime of t. Okay, so we have something that looks like that. And then finally, I'll write down the completely expanded form. So that would be the integral from a to b of, and to take the magnitude of something, you square the components. So we're going to square each of these individually, and we're going to add them together. Okay, and finally we have our z prime of t being squared. And then, because it's magnitude, you have to take the square root. Okay, and we have our dt sitting at the end. All right, so this is what you'll have to do when you're given a vector value function, so an r arrow of t, and it asks you to find the arc length from t equals blah 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 a to t equals b, some other number, right? And so you'll take the derivative of each and square them, and then kind of just plug them into this formula at the bottom here. Okay, so another way we can write arc length is as a function of t. Okay, so the way we do this is say s of t, and then instead of a to b, now we have a to t, because this is the thing that is varying. It can differ. Okay, and then we'll just replace r prime instead of t, now we'll just replace it with a u, because we want to be able to plug in that t later on without having another t already there. Yeah, it's just a matter of notation at this point. Okay, so this is, now this becomes the distance traveled, or the distance on the path traversed, right? So distance traveled by, or after, I'll say after time t. After time t. Okay? So that's what that signifies. And again, now in this form, it's called an arc length function. Okay, because now we have our s depending on t. Arc length function. Okay, so now that we went over arc length, I'll kind of segue into talking about speed. How does it relate to speed? So speed is the rate of change. So I'm just going to abbreviate rate of change, ROC, of distance traveled. Distance traveled. And then here's an important part, with respect to time. Okay, so what this means is that we have a rate of change going on, so that'll be a derivative of something, and then it says of distance traveled with respect to time. And this second part here, what I'm going to underline now, that looks basically like this part over here, right? Distance traveled after a certain time. So what speed is going to be is speed is going to equal the derivative with respect to time, of course, of the arc length function. Okay, so if we plug that in to the other side, if we ddt the right side, that means that we're ddting an integral from a to t of r prime of u, and then du. Okay, and on the right side here, according to the fundamental theorem of calculus for vector valued functions, now we have that these basically cancel out, but you plug in that t in the variable spot. So we have that speed, which is also denoted as a little v of t. This is not a vector valued function, it is a scalar valued one. Okay, so it doesn't deserve an arrow, or it doesn't get an arrow. Okay, so this turns out to be simply the magnitude of r prime of t. Okay, so this is our speed, and it's good to note that our velocity, so I'll just draw a little contrast here. So velocity is a vector, right? So velocity vector v of t is equal to r prime of t, and this is the vector form. And then basically when you take the magnitude, when you take the magnitude of this r prime of t, if you take the magnitude of the velocity, which is likewise the same, right? Then you get the speed. Okay. So these are two important equations to remember, these two at the bottom. So speed is equal to the magnitude of r prime of t, and velocity is that r prime of t at any given t.